Section 4.1, Direct Proof and Counterexample. So let's talk about what is proof. Basically, a proof is a series of arguments that follow logically to show us a mathematical property is actually true. So, for this class, we are going to have all of our basic rules of algebra. So, for example, A equals A. You do not have to have a separate line for that. We assume that. If A equals B, then B equals A. You do not have to say that. That's assumed. You may use substitution where valid. And we're going to talk a little bit more later about being closed. But when we say the integers are closed under addition, that means if you add two integers, your answer is also an integer. Now we are going to need some definitions to start out with. So let's start with even, odd, prime, and composite. Let's begin with even and odd. So we're going to say n is even. That means n equals 2k for some integer k. One important thing in proof, anytime we introduce a variable, we want to say what type of number that variable is. So we can't just say equals 2k and nothing else. We have to say that k is an integer. And similarly, n is odd. We'll write that as n equals 2k plus 1. You can technically define it as minus, but plus is usually just a little easier. So let's use that definition real quick to discuss a few options. Is 0 even? Yes, it is, because I can write it as 2 times 0. Is negative 301 odd? I can write it as 2 times negative 151 plus 1. So yes, it is definitely odd. If a and b are integers, is 6a squared b even? Well, I'm going to write that as 2 times 3a squared b, and that 3a squared b is an integer, so that's 2 times an integer. That is even. A and b are integers, is 10a plus 8b plus 1 odd. So again, I'm going to do a little rewriting. I've got 2 times that quantity 5a plus 4b, and then plus 1. That quantity is an integer, so this is the form of an odd number. And finally, is every integer either even or odd? And yes, that is a slightly more complicated proof, which we're not going to hit now, but it is yes. These types of ways that we are rewriting are what we are going to see as we start getting into some of these proofs. Let's get two more definitions. Prime. We say n is a prime means for all positive integers r and s. If n equals r times s, then either r equals 1 and s equals n, or r equals n and s equals 1. Do note this means that n cannot equal 1. Again, 1 is not a prime number. And composite means there exist positive integers r and s, such that, again, n equals r times s. And you'll notice r is greater than 1 and less than n, and we'll say the same for s. So those are our nice formal definitions. Again, we've said this a number of times, is 1 prime? It is definitely not prime. A prime has to be greater than 1. Is every integer greater than 1 either prime or composite? Yes. And this is actually one of our fundamental theorems of algebra, actually of arithmetic. We'll talk a little bit more about it later. And then let's write the first 6 prime and then the first 6 composites. Our first 6 primes are 2, 3, 5, 7, 11, and 13. And our first 6 composites are 4, 6, 8, 9, 10, and 12. All right, let's start by proving existential statements. Now remember, in existential statements, it only has to be true for one number. So as long as I find one number that makes something true, that's all I need. And we sometimes call that constructive, because I'm finding one example where it works. All right, let's try one. Let's prove there is an even integer n that can be written in two ways as a sum of two prime numbers. Now there's a lot of possibilities. I'm going to pick 10 though, because I can write that as 5 plus 5, and I can also write that as 3 plus 7. This is the entirety of my proof. Again, an existence proof, as long as I get one number that works, that's all I need. Let's try another one. Suppose that R and S are integers, and then let's prove there is an integer k such that 22R plus 18S equals 2k. So here I'm going to let k equal 11R plus 9S, and if I then multiply that by 2, that will work. So again, as long as I've got one example for an existential proof, that's all I need. And there's a general some statements there that we'll talk a little bit more about later as well. Now, universal statements, those are the for all, those are hard to prove. We will start doing them later, but they're going to be a little bit more effort. However, to disprove them is quite easy. We're going to use a counterexample. What that means is I only need to find one number where my statement doesn't work. So again, I want something where it's false. So let's see what that looks like. Here's my statement. For all real numbers a and b, if a squared equals b squared, then a equals b. So because it's a for all, if I can come up with just one number where that doesn't work, that's all I need. Again, there's a couple things we could pick. I'm going to pick 1 and -1. And as you can see, there's a couple other possibilities you could try, but 1 and -1 will definitely be enough to show that. And there is our counterexample written out a little bit neatly so you can see that. Again, we do want to be very clear about what the counterexample is, and we do generally show enough detail that it is very clear that the counterexample did not work. Alright, so let's actually look at proving a universal statement. There's a couple methods we can use. The first is called the method of exhaustion, so called because it's exhausting. Now this one, we've got for all integers n, if n is even and is between 4 and 26 inclusive, then it can be written as the sum of two prime numbers. Now there's a lot of numbers in that list, but it is a limited number of possibilities there. So basically, I've got every single one of those numbers, those evens from 4 to 26, and I have written them as the sum of two primes. So it's a little bit exhausting, but I can do that. What we are going to use most of the time is we call something the general particular. So I'm not picking a specific number, it's an arbitrary, random number, but it does have whatever properties that we're talking about. And usually we are going to talk about something with very specific properties. Here's a general talk about a little trick that you may have seen people use. And then how do you know the number is 7? That's because we are picking this arbitrary number. So we're going to use a box or an X to see how something like this would work, where you can see these are the instructions that you would give the person. This is what it's going to look at algebraically. And the way it ends up working is you get 2x plus 7 minus 2x, and because the 2x's cross out, you are always going to get 7 no matter what number people actually pick. Alright, so we're going to talk more about methods of direct proof in the next few sections, but first of all, in general, we want to express the statement proved very neatly. And again, we are going to always start by supposing that x is a particular, arbitrarily chosen element of D for which the hypothesis is true. And we are then going to try and get to Q by using definitions, by using the basic algebra and mathematics we already know, and possibly our rules for logic as well. So let's actually look at a direct proof. First thing we'd like to prove is that the sum of any two even integers is even. Now we already pretty much know that's true, but how do we show it? Now I'm going to skim past these pages. This is your textbook author describing the process. behind this. So again, I am skipping over this. And I am going to pull up my full proof. So there's my theorem, here's my proof. So I'm always going to start by stating what type of numbers I have. So notice I start by saying that R and S are integers. And because we want them even, let's use the definition for even. So R equals 2m, S equals 2n. Remember, anytime I make a variable, I have to tell what type of number that is. So m and n are integers. Also, because R and S are different, make sure to label them with different numbers. Don't call them both 2m, because that means R equals S. Now for proofs, we know what we're trying to end up with. So I usually jump straight to, well, what is this thing I'm trying to prove? Here I want the sum, R plus S. So if we add those two together, well, I can write that as 2 times that quantity m plus n. Now that, I called it t here for short, that is an integer. Remember, if we add integers, I get an integer. So I can write R plus S as 2 times an integer, and that is my definition of an even number. So this is our first example of a nice full proof. How do we get started with proofs? Again, some of our hints are to always start with that first sentence. Always start with your given. So if you've got something like this, I may have no idea what a complete bipartite graph is, but I know that I want to start with that. So I definitely want to show that whatever I'm starting with, this G is a complete bipartite, whatever that is. And I know that my last line is going to say that it is connected. So even if I have no idea what goes in between, I know where I'm starting, and I know where I want to end. So again, we know we're going to start with that complete bipartite statement. We don't necessarily know what goes in the middle, but we know what our last statement is also going to look like. So a lot of your homework problems will be fill in the blank type problems, and let's see an example of what that might look like. So here is our theorem for all integers R and S. If R is even and S is odd, then 3R plus 2S is even. And again, we've got a couple comments here from your author to kind of help you figure out where we're going with this. And you'll notice we've got at least one blank here. We've got another blank here. And finally, I've got a blank here. So pretty much your author is giving us the proof. All we have to do is justify all of these sets. So my very first one here, R equals 2m, well, that is my definition of an even number. And we can do that. We've also got the definition for an odd number for my S value as well. Our first step in here, that is our substitution step. Instead of writing R, we're writing what R is. So there's our substitution step. We know T is an integer because those are integers and because the integers are closed under addition and multiplication. And finally, that final statement, we've got 2 times an integer. That is our definition of an integer. And again, there's how I would write that proof out, all put together with all of our steps in there. And that is everything in section 4.1.